Hi guys, in today's video we are going to talk about a very specific topic. I recently got a question where the writer was asking what type of RCD is required in his off-grid system for the AC side as a protection. Many times I can hear or see the claim that people say every inverter installation requires a Type-B RCD to protect the AC installation, and this is what we are going to look into today. And I already want to point out something especially for our US viewers, because there seems to be no equivalent in the North American power system which is talking about different types of RCDs, right? You have the GFCIs, and those seem to be, correct me if you know this better, they seem to be all the same type, which you will see later on, compared to the RCDs, more or less the basic type. But when we are looking into RCDs, there is a lot of different types, and we are going to talk about it very soon, what all these types are meaning, and then we are asking ourselves the question, is it really necessary that every inverter, off-grid system, on-grid system has to install a Type-B RCD? Okay, so please bear with me if you're interested. It will be sometimes a little bit easier, sometimes a bit more complicated when it comes to more specific, but I think that we are going to understand at the end what all this is about. So what is an RCD, RCCB, a GFCI? These are many different abbreviations for mostly the same kind of device. We have a device in our AC installation which is measuring current in, current out, and is calculating residual current. And if this residual current is coming out of limit, then this device will disconnect our AC circuit and protect for, can be equipment protection so that you can avoid fires, but also it can protect humans from getting shocked. RCDs are already on the market, maybe for the basic types, for 40-50 years, and the most modern ones, the better types, they are Type-B, for example, are in existence for around 20 years. And we have to see this from two different perspectives. Perspective number one, which is the primary perspective, is how does the RCD react for certain loads, and that is what is determining normally the type of the RCD. And then our second perspective is how can a RCD be used to protect in certain cases when we're using power inverters to generate power and then use it. Let's look into the details. I have several papers printed out here, so we are going through this and then hopefully get some more understanding about this matter. Right, so the type of an RCD is usually represented by one or more letters, so it is called a type A, C, A, F, B, G. There's many different types and subtypes, and also by a symbol. And if you look on the RCD, we can then also find it somewhere in the name of the RCD, and then also here the symbol must also be printed on the front of the device itself. So you see the basic types like the Type A, C, and some countries also have a Type G. Every different type If you start at the basic and they go up to the higher level types will always include the features of the previous types and then just include something new again, a new feature. And what that means is that the device will recognize different styles of residual current. So the basic types basically means you have our sine wave in, which is 50 Hz, 60 Hz, and then if you have a ground fault in the circuit, then there will be a residual current which is measurable, and in the basic types that residual current should also look like a sine wave. Right? So this is for all the normal types of loads, resistive, inductive, capacitive loads. If you put a sine wave into your load, if there is a fault inside that device, the residual current will also represent a sine wave, and for this the RCD is built and designed. It will easily recognize this and then switch off the circuit. So the next type is then the type A, and additionally to the normal sine waves, it can also recognize pulsed DC. So that means there is a rectifier somewhere in the device which is connected, and if there is a fault somewhere in the later stages, then the residual current could also look like a pulsed DC wave, like you can see here. And this will be then recognized by the RCD. Next level, next type is then additionally high frequencies. We will then later on see the details about every type, and then the best types at the moment are the type B or type B+, which is then also including DC components in the residual current, which can then be detected. Let's initially look from the perspective of our application of the load which is connected to our power source, which type of RCD would be required. If we take our basic type AC, the types of load there are resistive, inductive, capacitive loads, usually without any electronic components, so any sorts of lamps, resistive elements like heaters, or just simple motors like an induction motor, something like this, right? So every time you put AC power into that appliance, AC current will be the residual current in case of a fault. For the type A is for single phase equipment with electronic components. That would be kind of normal washing machines, induction hobs, lighting controls, dimmer switches, EV charging installation, etc. Here somewhere in the circuit are diodes, rectifiers, which are turning our AC sine wave, which is coming into something different, but nothing too sophisticated. This is then still easily recognizable by the type A RCD. For the type F, I said there are now high frequency components inside there, and this is now in case of frequency controlled equipment like modern domestic appliances containing synchronous motors. So this can be washing machines, dishwashers, some air conditioning controllers using variable frequency speed drives. So for the type B, then everything what is three-phase and single-phase electronic equipment. So loads with three-phase rectifiers, variable speed drives, UPS systems, inverters for speed control, drives and inverters for supplying motors for lifts, pumps, machine tools, etc. And then also an interesting point for us, maybe installed in PV supply systems without at least simple separation between AC and DC side. And this we will later on look in detail. This is the case we are talking actually then today about. Let's look into the types of RCDs in detail. Type A, as I said, here we can see the schematics. There is somewhere in the circuit will be diodes which are cutting away parts of our sine wave, and we now only have half of the sine wave in this case, and this type of leakage, right, when the leakage occurs here after the diode, then this can be then also recognized by the RCD without any problem. The type F, as we said, single phase circuit supplying frequency inverters for speed control. We have in our schematics Ln goes in, we have a full bridge rectifier, means that here now we have our DC side, and after the DC is generated we have an inverter again which can make our variable frequency and thus make our speed control of the synchronized motor. And so this could be then frequencies beyond our 50 and 60 Hertz, and the RCD should also recognize any leakage in a system like this. Type B RCDs is similar to the type F, just that instead of only single phase we can now cover three-phase circuits with this one. So if you have a three-phase rectifier and then again DC inverter and variable speed drives, for example, and then additionally to this it can recognize DC leakage current, and for that one we will then have to especially look when we are talking about inverters. As you just saw, the main reason for the choice of the type of an RCD is the load, the application we are using it for. But now there is the claim that every solar installation is requiring a type B RCD at the AC side. So let's have a look from where that claim is coming from. Document is from the company SMA. SMA, as you know, is a tier 1 supplier of inverters of all sorts. And we are looking now into the regulations. This is DIN VDE, this is the German regulation, or the IEC, that's the international counterpart. So both of them are pretty recent, so this regulation is probably not very old. And it is saying a residual current device of type B must be used for the protection of the AC circuit. An exception to this requirement applies if the inverter manufacturer approves the inverter for other RCD types. So now SMA states for their own inverters, many SMA inverters are approved for the use with residual current devices of type A. A list of these inverters can be found in our manufacturer's declaration, etc. So this would be for types, for example, for type Sunny Boy, Sunny Boy Storage, Sunny Island, Sunny 3 Power, etc. So here we can already see that this rule that a type B must be used does not apply for every inverter. But we have a even more detailed document from Schneider Electric, and let's look into that one. So here Schneider Electric, another inverter manufacturer, is giving us more details. Let's go through this one. So depending on the design of the inverter, it may or may not provide a current path through which DC residual currents can flow in the AC circuit. An inverter with isolation between the AC and DC circuit cannot pass DC residual currents through the AC side. An inverter without isolation can pass DC residual currents through to the AC side, unless the design of the inverter prevents this in some manner. So now you can already see here what all this story is about. It is about how inverters are designed if DC can somehow come into the AC side, and this need to be recognized so that there cannot be dangerous residual currents on the AC side coming from a fault somewhere in the DC circuit. This problematic is there for so-called transformer-less inverters. A transformer-less inverter is taking the DC from the PV input, switching it through a lot of electronic and filters, and is passing this out as an AC output. But there is nowhere in between there is a galvanical separation, which would be there if there is a transformer built into this unit. If you are talking about transformerless inverters, so every grid-tied, grid-interactive inverter nowadays would be almost certainly a transformerless. Every off-grid inverter, which is a low-frequency inverter, you know, those have these massive transformers built in, will most probably be a transformer-based inverter, which does not have this problematic. And you know, those high-frequency inverters, you would really have to find out by the manufacturer what sort of design that inverter has and if this applies to as a transformerless or a transformer-based inverter. Let's have a look at this inverter board here. So this is a salvaged board from a WVC600, a Chinese micro inverter. I have a video about it on my channel, how crappy these things are and how quickly they get broken. But that's not the point for this video. If you look at this inverter design, it's a very traditional design. And here on the down, this is the DC side. The transistors are missing because they had a short on the DC side. And here the AC side. And if we turn this over, then we will see here a very clear separation on the circuit board already between the DC side and the AC side. So sometimes even some cutouts on the PCB, and there is not a single trace from this side to this side, and the only area which connects the DC side to the AC side is here via these two transformers. This is a galvanic separation, and there is no way for DC, if it comes into the AC side via a ground fault, it can return on the other side via the transformers, right? Okay, so let's continue in the document. Consider a PV system containing a non-isolated inverter and an AC main circuit with an earth grounded neutral. So we have a neutral to earth bond, of course. A ground fault in the DC part of the system will create DC residual currents that can flow from ground into the AC main circuit by way of the AC neutral to earth connection and back to the DC circuit through the non-isolated inverter. So we have a fault here somewhere in the DC side. It goes via grounding to our neutral to ground bond and then back into the inverter, back to the DC side, and so we have a closed circuit there. Let's continue. The RCMU stands for the Residual Current Monitoring Unit. So there is an electronic circuit inside the inverter which is trying to identify those sort of leakages also, right? The RCMU in the inverter will detect this current. However, The RCMU is allowed to be set for residual currents much higher than the 6 milliamp. 6 milliamps is usually what the RCDs are set as maximum tolerated value. Therefore, a Type A or Type AC RCD would not be acceptable, right? If the RCMU is set to trip at 6 milliamp or less, then this would already be handled by the inverter, and this is then acceptable. The text from the regulations again. Where an electrical installation includes a PV power supply system without at least simple separation between the AC side and the DC side, an RCD installed to provide fault protection by automatic disconnection of supply shall be Type B. Where the PV inverter by construction is not able to feed DC fault current into the electrical installation, an RCD of Type B according to our norms is not required. So as you saw, this regulation, the requirement to use a Type-B RCD in a solar installation purely comes from how the inverter is designed. So as soon you have a galvanic separation between AC and DC side, there is no possibility for DC leakage current on the AC side, and Type B is not required if it's not required by the load anyway. So whenever you have only simple loads connected to your off-grid inverter, and you know your off-grid inverter maybe because it's a low frequency inverter or because the manual tells it that you can use Type A RCDs, then you can just skip the Type B RCD. When would you still want to use a Type B RCD? Well, whenever you are in doubt, you don't know exactly what your inverter type is, and you cannot measure it out by measurement if AC side and DC side is galvanically separated, then use a Type B RCD. And you know, if the extra double or triple the cost for the device of the RCD, because it's a Type B, it does not matter much, then just use a Type B RCD. But you see, for the viewers in the United States, you also have modern appliances, modern equipment, variable speed drives, switch mode power supplies, UPSs, etc. But you are not using RCDs in this way. You have your GFCIs outlets typically, which is directly in front of the appliance. So I have no idea, maybe you can tell me how these sort of problems are solved or tackled in the United States. Maybe the appliances itself have to have some sort of protections inside, and on inverter side, maybe the inverters in the United States have to be built differently. So I don't know. Maybe if you know it, please comment on the down and tell us what you know about the situation in the North American system. So that was it about this issue. There is no regulation anywhere which says that a Type B RCD is required no matter what. Okay, so I hope I could clarify something for you here. Thank you for watching the video. Please subscribe to the channel, like the video, and I see you next time.